So let's take a minute now to assess where we're at right here, and let's just take a little bit of time to define principal domains and ranges of our secant, cosecant, and cotangent functions, in addition to our normal functions sine, cosine, and tangent, because we should have some idea of what these values are going to be. So in our cosecant function, we're basically mimicking what happened with the sine function. With the sine function, recall that we went from negative pi over 2 to positive pi over 2, and the only difference that we have in this particular case is that right at 0, we have a vertical asymptote. And so we have to make sure that we include that fact in our principal domain. So I'm going to write it in interval notation just to make it easy. In interval notation, our principal domain goes from negative pi over 2 to 0, doesn't include 0, and then goes from 0 to positive pi over 2. So it's, in essence, this is almost the same as the sine's principal domain, except we don't include 0 due to the vertical asymptote. Secant, similarly, secant includes a vertical asymptote at pi over 2, but other than that, because it is a reciprocal of a cosine function, I'm being very careful to say reciprocal, not inverse, be careful. The reciprocal of the cosine function is secant, and over our interval from 0 to pi, we just don't include pi over 2. So our interval, similarly to our cosecant and in some ways to our cosine, is going to be the interval that goes from 0 to pi over 2 but not include pi over 2, union with the set from pi over 2 due to that vertical asymptote out to pi, and including pi at the end point. One more, and this one goes with our cotangent function, and let me show you the asymptote here just as a reminder. In this case, the asymptote is at pi, and unlike what happens with tangent, our interval is going to go from 0 to pi, so we're going to limit our principal domain interval to go from 0 to pi, but this time not including the endpoints. And so this is actually, in a way, more similar to cosine as far as that principal domain is concerned. So having these definitions in hand allows us to write some information about our inverse cosecant function. So we can imagine an inverse cosecant function, y equals the inverse cosecant of x, where x now is was the range of this guy, and so our range went from negative infinity to 1 to negative 1, pardon me, union with the set from 1 to infinity. This becomes our domain of our inverse cosecant function, and the range of that inverse cosecant function becomes this principal domain that went from negative pi over 2 to 0, but didn't include 0, union with the set that went from 0 to pi over 2. In a similar fashion, if we have y equals our inverse secant, we're going to have a domain that, like the domain of the inverse cosecant, goes from negative infinity to negative 1, and includes negative 1, and then is a union with 1 to infinity. And the range of our inverse cosecant will be the range that goes from 0 to pi over 2 due to that vertical asymptote, which becomes a horizontal asymptote in the inverse secant function, union with the set from pi over 2 to pi. And finally, we look at our cotangent function, and our cotangent function, when we look at the inverse inverse, let's see if I can spell it today. If we have y equals the inverse cotangent of x, then in this case, the domain will be the set from negative infinity to positive infinity, because this was the range of our original cotangent function. And the y value is the range of this inverse cotangent function is going to be the same as our domain of our original cotangent function, and that will be from 0 to pi. And so our angles, if we had an inverse cotangent function, would be in the first and second quadrants, kind of similar to cosine. Okay, more video stuff to come.